Hi, everyone. Thanks a lot for joining. It is my great pleasure to introduce today's speaker, Professor Joshua Yang, who is the Arthur Freeman Chair, Professor of Electrical and Computer Engineering at University of Southern California. Professor Yang joined USC in 2020, coming from the faculty of the University of Massachusetts Amherst, specializing in post-CMOS hardware for neuromorphic computing, machine learning, and artificial intelligence. He has published many groundbreaking research papers in these domains, and his innovative work has led to granting of over 120 US patents. Professor Yang is the Associate Editor of Science Advances on Neuromorphic Topics and the founding chair of the IEEE Neuromorphic Computing Technical Committee. He serves as the director of an Air Force-funded Center of Excellence on Neuromorphic Computing at USC, and he is recognized as a Clarivate highly cited researcher and listed among the top best scientists in the electronics and electrical engineering category by research.com. He was elected Fellow of the IEEE in 2022 and of the National Academy of Inventors in 2023 for his contributions to resistive switching materials and devices for non-volatile memory and neuromorphic computing. So it is a tremendous pleasure to be able to hear from him today. Thank you for joining us, and we're excited to hear your talk.
Thank you. Yeah. Thanks, Finance, for the kind invitation and the introduction. And good afternoon, everyone. It's great to be here, see a lot of old friends. And I didn't expect, Friday afternoon, there are so many people still interested in this topic. Thanks for coming. So what I'm going to talk about neuromorphic computing with different type of memristors. Okay. So speaking about neuromorphic computing, actually 1.5 months ago, I was in a conference, and during lunchtime, I was at a lunch table with a bunch of editors from Nature research journals. I was trying to advocate neuromorphic and trying to talk about how exciting it is, how promising the future is. And then one of the editor, because camera, I'm not going to name it. So suddenly said, didn't Giacomo Indeveri just wrote a paper said neuromorphic is dead? So I was like, what? By saying that, actually, I exposed my ignorance of two aspects. First, I didn't even know that paper exists. Second, I didn't know why someone like Giacomo would say something like that. So then after that conversation, you can imagine immediately I went to my hotel room and found out that paper. And here it is. It does say neuromorphic is dead, but it also says long live neuromorphic. So if you read it, it says, actually, it blames the recent shift toward the digital and AI-centric approach. In that sense, he thinks the old definition of neuromorphic is dead because of that shift, but he blames this trend, and he advocates for us going back to the original principle of neuromorphic and emphasizing on analog, brain-inspired systems, and also the importance of fundamental neuron science for the future progress. So basically, in that sense, that's a long-lived neuromorphic. Okay, it still have a very bright future if you do it right. Okay, how to do it right? And if you keep reading, and at the beginning, he said the term neuromorphic was originally coined to directly emulate the biosystem, not simulate, right? And to mimic the dynamics of ion channels. So after reading to here, then I was much relieved. So because this is exactly something we have been doing in the last decade. For example, starting with this paper, we started to advocate that you can use Memristor diffusive dynamics to mimic the synapse faithfully. And more recently, we did it for neuron. I will talk about that later. So basically, it's good, okay? So neuromorphic is still alive, and we can talk about it and do it, right? So then what does neuromorphic covers? Obviously, it will cover the natural intelligence approach. So in this approach, you use spike-based signals, you use dynamic synapse and neurons, and you use the biological learning rules, right? But as Giacomo said in his paper, and there are a lot of people also trying to use neuromorphic to cover other types, like the digital AI-centric approach. In this category, you are using value-based signal instead of spike. After training, you have a fixed weights and static neuron, and you are using gradient-based learning, such as backpropagation, rather than here, such as STDP, spike time-independent plasticity. So in this approach, the mainstream computing platform, you use digital von Neumann architecture, right? So such computing platform bear almost no similarity to neural network. So in that sense, it is a simulator, of the neural network. It's the mainstream, though. It is something large scale you can use, but it also faces deep crisis of energy efficiency, right? And our long-term goal, of course, is to have the natural intelligence emulator, right, rather than just a simulator, and using analog approach. But that is a very long-term goal. It's not going to happen very soon at large scale. But there is a middle stage. So in this middle stage, what we can do is we can use some of the neuroscience principles, not all of them, but some, such as in-memory computing, analog computing, parallel computing. With only these three principles, for example, you can already get a very efficient AI accelerator. So to accelerate those computing, and in this case, of course, you use both analog and digital. It's a mixed signal system. So in the next few slides, maybe we can first look at why this type of approach, the digital mainstream platform, is in trouble, and how this can help, and why this is the bright future. So what's wrong with the digital system? The digital system, the biggest trouble, as everybody here probably know already, the digital hardware is way behind the demand of the AI, the algorithm needs. As you can see, everybody uses ChatGPT, I assume, right? But do you know ChatGPT is so power hungry, it uses 45 gigawatt hour daily for inference. So you may say, I have no idea what this means. Actually, this means 1.5 million household power consumption daily, just ChatGPT. Okay, that is actually more than 1% of the household in the US. And that will need 2 to 3 nuclear plants to power up just for ChatGPT. Google has a Google version and everybody. So you can imagine how much energy we're going to put in just those things. So basically, in the last few years, you can see the computing demand increased by 1 million times. But around the same time frame, the hardware improvement represented by the GPU of NVIDIA, it has made a lot of improvement. But even that a lot is about 100. Compared to the 1 million times demand, you have a huge gap. And that gap cannot be met by continuous increase, the computing efficiency just along the same direction using digital system, as you can see the trend, right? So you have to use some disruptive technology to do that. Okay, so question is, what's wrong with our digital system? And probably everybody know as the device level, Moore's law is coming to an end. We know that. And also, there is a memory war. because the processor performance is better than memory, and the gap between the processor and the memory is increasing with time, not decreasing. So this is called the memory wall. Memory is the bottleneck. And in addition, the Dennett scaling law has ended a long time ago. Basically, even if you can make the device smaller and smaller, you cram more devices on the chip, but the power density of the chip is not constant anymore. It increases dramatically, which means even you have a lot more devices on the chip, you cannot utilize them simultaneously anyway before you burn the chip. That's called the heat wall. Right? So those are at the device level. At the architecture level, the challenge is as big, if not bigger. That's the Von Neumann bottleneck. I think a lot of people should know here. So, in your phone, your laptop, everything, the mainstream digital system is built based on Von Neumann architecture, which means you have a separate processor from the memory. These two are physically separated. You store your data in the memory. When you need to process it, you send it to the processor, get it processed, you send the result back, store here, you take the next piece of information and to the processor to process. You do it in sequential. And that was perfectly fine in the past when the computing did not involve a lot of data. But nowadays, we know computing are all pretty much data-centric. So constantly shuttling data between the two units takes a lot of time and a lot of energy. It's just too much we cannot afford. That's a bottleneck called a Von Neumann bottleneck. And this is a digital system. Our world is analog, our data from the analog world. You have to digitize it first, then process it in the digital system. The analog digital conversion also is notoriously time and energy consuming, right? So how to solve those problems for the digital system? So we learn from something we know to be the most energy efficient computer. That's the brain. So then if you look at the nature, then you find a lot of our problems have been solved by millions of years of evolution in animals, in human beings. And the answers for many problems are already there, right? So how does the brain perform computing? It uses neural network. And the network is neurons connected by synapse. And the synapse is the memory here. So store the data in synapse, and the computing is done where the data is stored. So it is in-memory computing. So you don't need to shuttle data between the processor and the memory. So that is a very big deal. It's in-memory computing. Computing happens everywhere in parallel. It's a parallel computing. And it can deal with analog data directly. It's analog computing. So with these three principles, you can build an AI accelerator, okay, to be very energy efficient, high throughput. So there is more. And the brain is also known to be much more efficient in learning. It uses much less data, much less energy for learning, learn much faster. It is because brain is using the neuroscience principles for learning. Okay, very different from what we are using in AI. So with those principles included, then you will have something more like a natural intelligence emulator, right? So to include those principles into artificial system we build, we will need to have a new type of devices rather than just CMOS silicon devices. So there are a lot of types. Memristor is one of the leading candidates we have been working on. For those who do not know how Memristor works, it is shown here, simplified mechanism. You have two electrodes, and in the middle, you have an oxide material, let's say titanium oxide, which can be viewed as a semiconductor with wide band gap, okay? As a semiconductor, it has its dopant. the dopant here are oxygen vacancies. So the doped region are conductive. The undoped region has a metal semiconductor barrier, shaky-like barrier, give you high resistance. That's why the entire device now is in the off state. So the beauty here is the dopant are mobile, electrically mobile. So you can use the electrical field to move the dopant and also dope the top region and make everywhere conductive, then you get the on state. Right? And so if you want to change it back, you reverse your voltage polarity, you move the oxygen vacancy dopant back, you get the off state. And you can stop in the middle as well. So the oxygen vacancy is the dopant here, but you can use many other type of dopant with other type of dielectric material to make a memristor. So as you can see here, the dopant migration is critical for the function of such a device. So what determines the dopant behavior largely is the activation energy. For example, if you have a high activation energy, like oxygen vacancies in an oxide, the activation energy is high, and you need to pay more energy to move them to switch the device. And the good thing is after you switch the device, you move them, they like to stay there in a stable way so that you get non-volatility. So then when you do reset, you switch it back, move it back, you need to reverse your voltage polarity. You move the ions back by drift. So that's why we call this a drift memristor, right? So this type of device has very stable conductance levels. It can be used to serve as an AI accelerator, right, I talk about. So instead, if you have a low activation energy, such as silver in oxides, and the activation energy is so low, you need to use very little energy to move them, to switch them, but easy come, easy goes. So after you switch it, you remove the electrical bias, the ions can easily diffuse back to give you the reset automatically without electrical bias. That's a diffusion process for reset. That's why we call it a diffusive memristor. So this is a volatile type of device. It has a very interesting ion dynamics. Remember at the first slide, I talked about ion dynamics is very important for biological neural network. So this is very useful for something like a spiking neural network, and I'm going to talk more about that later. There's something in the middle. If you have an activation energy, not too high, not too low, and that gives you also very interesting behavior. For example, this is a traditional device with a high activation energy, oxygen vacancy as the dopant. So typically, you need a high switching current, and the switching can be abrupt. So those behaviors are not something you lack when you use the device for training in neural network. And interestingly, if you replace this tantalum with something else, like ruthenium, immediately you see the switching behavior different. And you can see now the switching need a much lower, 2 orders of magnitude lower current, and the switching on and off are much gradual. So those low current gradual switching is something you like to have when you use the device for neural network training. And this is oxide agnostic. As long as you keep ruthenium electrode, you change your oxide, it doesn't matter. You can see in this case, it gets similar switching behavior, low current and gradual switching. So it can be done with something else, like in perovskite material. I'm not an expert of this, but we have collaborators, they make this type of device. And it's supposed in such materials, mobile species is the iodine vacancy, which has a medium activation energy that gives you low current switching and can have gradual switching behavior if you do it right. Okay, so there are actually a lot of fantastic study along those lines in on this campus, such as in Belgia's group. They use different ion, proton, and make in the 3-terminal device and show very nice potentiation, depreciation, and show very fast switching behavior, and a lot more. And also in Joanne's group, they use some very interesting mechanism to control the ion dynamics. So they use dislocation and they use an alloying approach to make a much more reproducible device and control the variability. So there are a lot more. I know today, I'm supposed to talk about my work. So in our group, we have been, in the last few years, we have been trying to focus on using different type of memoristic devices for different computing applications. And some of the main results are listed here. And it can be categorized into 3 groups. In the first group, as shown here, we're trying to build the AI accelerator I talk about. And in the second group, we're trying to build a more faithful device to biological. So they're trying to make natural intelligence emulators. And in the third category, we're trying to interface it with sensors. I will talk about that. That is also an important direction. I will mention about that at the end. So, due to the time limit, I'm going to pick a few examples to talk about in each category. So the first category is to build an AI accelerator, in this case with drift memristor. And then I will talk about to build a natural intelligence emulator with diffusive memristor. And then last, I'm going to talk about how do we interface it with sensors using both drift and diffusive memristor. Okay. So the AI accelerator, I assume a lot of you already know the trick here. This is basically our accelerator is accelerating one thing, vector matrix multiplication, which may sound trivial, but it is a big deal for AI machine learning because over 85% of computing are pretty much nothing but vector matrix multiplications. So how we accelerate that is we can map a mathematical matrix into the conductance matrix of a memristor array by switching each device to a certain conductance. And then we can use a vector of voltage to represent the input data. And the voltage is applied to the rows, and we collect the current at the end of the column. So the current is the dot product of the input vector with the vector in the matrix. So this is because you are using actually Ohm's law for multiplication everywhere, and you are using Kirchhoff's current law for summation also everywhere simultaneously. So basically, if you think about this, it is in-memory computing, it's a parallel computing, it's analog computing. It implements the 3 principles the brain actually is using. So that's why it can lead to order of magnitude improvement in speed and energy efficiency. And to demonstrate this in hardware, we did it a while ago. We did show order of magnitude improvement in throughput and energy efficiency. However, for such analog computing, it also has its weakness. So the weakness is the precision. Okay? So in order to improve the precision, we have done something at the device level and also the circuit level. At the device level, it turned out that a memristor is not a resistor after all. It is noisier than a resistor. And if you switch the device to a fresh state, then you read it with a constant voltage, then you can see the current reading is quite noisy. You have the random telegraph noise. With such big noise, you cannot have many conductance levels very close to each other and still distinguishable. So fortunately, actually work with Professor Julie from MIT group. They did a theory analysis for us, and we understand the origin of the RTA, and we derived a simple electrical operation protocol to denoise it. And after denoise, you can see the resistance noise is now much smaller, like the red curve. Now you can have 2 conductance levels very close to each other and still distinguishable. So with that, we can get thousands of conductance levels from each device. That is demonstrated in a large array, memristor fabricated on CMOS made in the foundry. So that 11-bit precision is good enough for inference application, but not good enough for many other applications, such as training of neural networks, such as signal processing, such as scientific computing. To get even higher precision, we need to do something at a circuit level. And to do that, we designed an architecture and algorithm allow us to, in principle, obtain arbitrarily high precision by, we call it error compensation approach. So the concept is shown here, the circuit are shown here. I'm not going to go into detail, but rather by saying that the key is instead of using just a single device to represent a number, we use the weighted sum of multiple devices to do that. For example, if you wanted to represent a number, 1,000 microsiemens, you can program one device, and because it's an analog, always have error, let's say 10% programming error for those devices, then you end up with 900 microsiemens. Okay, so instead of keep programming the same device over again, hope you luckily hit on this target, which is not guaranteed, need many steps, and you just program a second device to compensate that error. You know the error is 100 microsiemens. You program the second device, you give it a smaller weight to make sure it converge. So then with, let's say the second device is happen to be programmed also with 10% error, then with this smaller weight, it end up representing 90 microsiemens. Then you add these two together, you have 910. 10 microsiemens away from your target. You can keep programming the third device with an even smaller weight, and you can get this device represent 9 microsiemens. Then you add them together with their weight, you get 999 microsiemens, and that drops the error from 10% to 0.1% by just using 3 devices, right? You can keep doing that if you need a higher precision. So the circuit overhead turned out to be quite affordable. And we made this demonstration in a foundry-made SoC. So here is a 12-inch wafer, and there are a lot of dies on it. Each die is a SoC. Obviously, I cannot bring the wafer there. I hope I have something here that is one of the dies. I think you can pass around. Actually, it's one of the chip we made with Memristor on CMOS. And each of the SoC has 10 neuron processing unit, and each NPU has 256 by 256 array. And then each of the device is capable of 1,000 conductance levels. So with the on-chip CPU, SRAM, and everything, you basically have a computer. You can program the chip to different neural network or different other things for different applications, right? So first, we use it for high precision scientific computing. In this case, we use it to do the magnetohydrodynamic system simulation. And you can see the comparison between a digital system and an analog system. The results are quite similar. The difference is you have order of magnitude higher energy efficiency for the analog chip. Okay? And because now you have high precision, you can use it to also process signal, not just neural network. For example, you can program the array into DFT, which is a discrete Fourier transform coefficient. And then this matrix can be used to process the input signal. The input signal here is, for example, a spectra. The signal is in a time domain, okay? Then this DFT can convert the signal from time domain to frequency domain within one shot. And then the frequency domain spectra represent the fingerprint of the input signal, and that fingerprint can be sent to a neural network, also made of a Memristor array, to do the classification. So basically, what you can do is to use the signal processing layer as the first layer of your network. You form a fused network to do the signal processing to the classification, all on the same chip, right? So in the next few slides, I'm going to show you how we experimentally demonstrate the DFT and then the neural network, then the fused network for signal processing in real time. And I apologize, we cannot hear the sound here. Basically, a student is playing a music here, and you can see the music, temporal spectra here, and that is converted by the DFT on chip here into spectral domain. That's a red curve you see here. And to compare, we also use the software to convert it. You can see the software and hardware result are quite comparable. So you're supposed to hear the sound, but you can see it from there. So this shows we can use it to do signal processing, right? DFT. And then to show the neural network on chip, and we do a real-time video edge detection. This is the video student is holding, and this is processed by software. This is the processed result by the chip here, and you can see they are quite comparable. So now we have the signal processing DFT, we have the neural network, we can combine them together to form a fused network also programmed on the chip, and then we can use it to classify a temporal signal. The sound is converted into spectral signal by the DFT layer, and then the spectra is classified by the neural network. All done in real time on the chip. And the monitor and the computer here is just to visualize the input and output. So as you can see here, the real time processing is something already demonstrated on the chip, even though it's not large enough to do large language model yet at this stage, but it is coming. As you see, there are quite a lot of Memristor effort now is going commercialization, as shown by this recent perspective paper. So that is something very close. Okay, now let's talk about something still far at the early stage. That is something like the natural intelligence emulator. For example, used by diffusive Memristor. So you would say, we don't know much about natural intelligence yet. How can we emulate it, right? And so the approach here is one of the approaches, which is bottom down, is understanding by building. So we're trying to build something, then we play with it. We're trying to use it to help us understand some of the bio principles. That's in order to do that, we need to have a lot of faithful building blocks to the biosystem. And actually, we published this in the special issue organized by Bill Gates in Chemical Review. It's a summary of our effort in this direction. So if you look at the biological network and the major component, synapse, soma, dendrites, and immediately you will see the ions, the ion migration, the ion channels are playing the critical role in generate their functions. So like in the first slide we talk about, we wanted to emulate the ion dynamics, okay? In order to build those components faithfully. So take a neuron as an example. The neuron key function is to generate action potential like this. And if you look closely how the action potential is generated, you would find that first you have an ATP pump that is pumping sodium ion out and potassium ion in, and to build the concentration gradient of potassium ion and sodium ion just in the opposite direction, the gradient. And then this neuron start to integrate input signal. Once the integration is over a threshold, then the voltage-controlled ion channel is open. Once this channel is open, remember we have the concentration gradient built by the ATP pump. Now the sodium ion flood in. Once the gate is open, the motion is driven by the concentration gradient, and that will increase the polarization, and then the sodium ion channel will close by itself. Even before this close, the potassium ion channel will open, then the potassium ion will flood out, also driven by its own concentration gradient. And that will decrease the polarization, and then the whole thing will go to a resting state, and the ATP pump is keep working, maintain this resting state. So in this whole process, the ion channel open and close is very important. So in order to build an ion channel emulator by a nano device, we use a diffusive memristor. And here you're looking at a snapshot of in situ TEM, showing at each moment when you apply electrical bias between the two electrodes of a diffusive memristor. You can see in the gap you have a silver doped silicon nitride oxide. At the very beginning, when you apply electrical bias between the two electrodes, and because you have a gap here, the current remains low. This process mimics the ion channel closed state. But it's even though the current is low, actually something is happening inside the device. You can see the silver are actually moving, and this is more and more silver accumulated here. This mimics the integration process of the neuron before firing. And then once it reaches threshold, you build a complete channel bridging the two electrodes, then the current shoot up. Okay, so that mimics the process. It generates action potential, the spike. And the channel size is about 4 nanometers in diameter. So interestingly, after firing, there's no electrical signal anymore, and zero electrical bias. You can see this filament reshape itself spontaneously into a sphere. So break this channel, and this mimics the process. The neuron goes back to resting state after firing automatically, doesn't take any energy. Right? So this is a diffusion process from here to here because there's no electrical bias. And so this gives us a faithful ion channel. And then we can also use a capacitor to mimic the membrane capacitor, put them together. You have a simple leak, integrate, and fire neuron. Okay? So as shown by this experimental data here, it does show the leak, integrate, and fire. So with this, it's a more capable neuron. It's a dynamic neuron. Now you can combine with synapse, and you build a neuron network full of memristors. And so you only have 8 neurons here, small neuron network. But because the neuron itself is much more capable, and it can perform unsupervised learning. And we were very excited to show for the first time you can experimentally demonstrate unsupervised learning with the memristive network. And so this is because now you have a more capable neuron. But even this neuron, like I said, it just has a very simple function, like a leak, integrate, and fire. But we know in the real neuron, there are a lot more functions. Okay? For example, it can also cascade signal from one layer to the other. Neuron is an active device. So it also has intrinsic plasticity, it has a refractory period, it has stochasticity. So in order to capture all these 6 key functions, if you build your neuron with a traditional CMOS, it will be a bulky circuit like this. You will need 24 transistors and 3 capacitors. And we know we have so many 10 to the 11th neurons in the brain. You cannot afford to have such bulky circuit to represent just one. And it will cost a lot of energy and area. So fortunately, now we have the dynamic device, like a diffusive memristor. We can build a neuron with only 3 components, but still capture all the 6 key functions. Okay, so in this neuron, you have a transistor, and you have a drift memristor and a diffusive memristor. Because memristors are typically much smaller than a transistor, So you can build the memristor on top of the gate, build a 3D neuron, and the entire footprint of this neuron is no bigger than a single transistor. Okay, so that's easy to say than done. Actually, it took a student almost a year to successfully integrate the two memristor, one drift memristor, one diffusion memristor on top of a transistor, and show you can get this very nice neuron behavior. And if you look at it in detail, we experimentally show that such 3D neuron can show the leaky integration, firing threshold, cascade propagation, intrinsic plasticity, refractory period, and stochasticity. The 6 key functions all come from area with just a single transistor. The reason is you utilize the ion dynamics in simple devices. So we do not have a large array of this yet. And in order to understand the array level performance, we build a model that can faithfully reproduce the neuron behavior. And with that model, we are able to, in simulation, build a large recurrent spiking neural network with thousands of neurons and multiple layers. So with this recurrent spiking neural network, we are able to classify spiking Heidelberg digits. Basically, it's a spoken version of MNIST. So we can see the neural network can do a decent classification with good accuracy of those spoken digits. But we also show if you remove one of the 6 neuronal functions from your neuron, your network performance is going to be affected negatively. So that shows all those functions are actually useful for the neuron. Okay, so we also compare the memristive neuron with the neurons in the living monkey. And with our collaborators, of course, they did the experiment to measure the neuron firing behavior in different regions in the monkey. And as you can see, these are the memristive neuron, and qualitatively, they are comparable. So basically, this is all due to the ion dynamics you have. Okay, now let me switch gear, talk about the last part. Is integration with the sensor. So if you think about the natural intelligence system, they evolved by better deal with their environment. Okay, right? So that means they have to interact with the environment very efficiently. So this comes from the fact that the natural intelligence usually seamlessly integrate sensing, encoding, and learning all together. And for example, you have different sensors, and they generate sensing signal. Then the signal will be encoded into spiking signal, either many spikes with a different frequency or a single spike with a different spike timing to represent the data. And such spike signal is going to be sent to the brain, which has the neural network to do the sensor fusion and also the learning, typically unsupervised learning. To mimic this system in an artificial system, you will need to have sensors, then you will have a spike encoder, and then you will have a neural network to do the sensor fusion and the learning. So if, again, you do it with the CMOS circuit, because CMOS circuit is not designed to optimize for this purpose, and you are going to need a bulky circuit like this just for encoding, okay, encoding signal. And again, using the new type of memristor, diffusive memristor, we show that we can realize a spike encoder with just a single diffusive memristor, okay, rather than such a bulky circuit. And as experimentally shown here, you can have a sensor, in this case, let's say a pressure sensor, then a diffusive memristor. Circuit-wise, it looks like this. You have a sensor. When you have a pressure, it generates a voltage. That voltage is going to turn on the diffusive memristor, generate a current spike. Okay? If the pressure is high, then the voltage here is high, then the memristor is turned on quickly. It generates a spike within a very short delay time. That's a spike timing. If the pressure is low, then the voltage is low, then the memristor is still turned on, but only after a long delay time. That's a long spiking time. So basically, this diffusive memristor convert the pressure amplitude into a spike timing, right? That's a spike encoder. And if you think about this, you don't need external power. And the pressure sensor itself powers the memristor. It's a self-powered system. And it's event-driven. Only if you have an event, something happens. And it's very energy efficient. So this is not just for pressure sensor. It works for many sensors, such as temperature sensor, such as light sensor, as we've shown here. For the light sensor case, a single diffusive memristor, it converts the light intensity into spike timing. Okay? It's self-powered, event-driven. So now we can combine those components together to build a sensing and learning system. As shown here, experimentally, we have a pressure sensor. Oh, that's a pressure sensor. We have a light sensor, and we have a diffusive memristor. Two of them serve as a spike encoder. We have a drift memristor here, serve as the synapse for the learning part. And then we use this experimentally demonstrate some learning, like input timing dependent plasticity. This is a learning rule commonly observed in the biosystem, like STDP. So this learning rule actually generates the biggest weight change if the two spike signals are synchronized. So use something like this, we can find many applications, such as we use it as a lightning detector. So because a lightning event, you have light, you have sound, and the sound is like the pressure. So you can use such a system to, in simulation, we show we can use it to distribute it in a large area to detect the lightning event, which may not be important here, but it's important for where I come from. You know, in California, each year we have a lot of wildfire caused by lightning event. We want to know the lightning, distribution. So, but anyway, if you look at this system, we don't need external power. It is use the sensor itself to drive the system. It's self-powered, and it naturally do the sensor fusion with the multimodal sensor. And the learning is unsupervised learning, and also, realized inside the system with only few components, right? Okay, so to summarize, I talk about, for the memristor, the activation energy of the mobile ions are important. It largely determines the memristive behavior. And if you have large activation energy, you get a drift memristor. It's non-volatile. Reset has to be done by drift, but it shows stable, dense conductance levels with high precision. It is good for AI accelerator application. If you have low activation energy, then you get a volatile device. The reset has to be done by diffusion, and it shows desirable ion dynamics. It will be very efficient for a natural intelligence emulator. And both diffusive memristor, drift memristor can be used directly interface with the sensors to enable efficient and intelligent sensing system. So after all, I think neuromorphic computing will be long-lived. Okay, that's another takeaway message if you don't remember anything else. So I'd like to thank my coworkers, postdoctors, and as shown here. And I also like to thank the sponsors for the work. Thank you for your attention.
For the great talk. Thank you. Wonderful talk.
Thank you.
So we have time for questions. Anyone wants to go first? There are also, go ahead.
Thank you, Joshua. Thank you, very nice talk. And I have a question about the capacity of the in-memory computing element. So if the capacity of this technology is not that large than the large language models or media scale models, it's hard to convince ourselves that's in-memory computing.
Yeah.
So I want to ask, what's the ideal scale or ideal capacity of single chip level and also single array level in memory computing technology?
Right, yeah. Okay, then that's a very good question. So, so far, we are, each cell is 1T, 1R. It has one transistor, one memristor. So the density is limited by the T. By the transistor. You know, as everybody knows, even if you use the 3 nanometer transistor 3 nanometer technology node, a transistor you make is still going to be 3,000 nanometer square. But the memristor itself can be as small as 3 nanometer by 3 nanometer. We even showed 2 nanometer by 2 nanometer area for a single memristor. So memristor will be much smaller than the transistor. So the density now is limited by that transistor. Then you can think at this stage it will be a DRAM density. DRAM is 1T, 1C, right? And so DRAM you can stack, right? You can stack and the high bandwidth memory. But the issue there is once you stack more, then the energy consumption will be too high, the heat dissipation will bother you. You cannot go probably more than 16 layers. So those devices, they will have a much lower energy consumption. So they probably afford more, stacking layers. And also people trying to develop 1T multiple R. Okay, so in addition to that, you should also think 1R, you can have 11-bit precision, maybe even higher. So that equivalently, 1T, 1C, that is only 1 bit. This is one cell, one transistor region, you have 11-bit, right? That density, so if you think about that, actually the density is pretty promising. We can do a larger one, and we can scale it, down to 5 nanometer, 3 nanometer, and eventually, I think a single chip, we can probably have, let's see, Giga will be something for sure. Yeah, we can do. Yeah, Giga. Yeah. But still, large language model will need more than that. Yeah, so we will need multi layers. But for many edge applications, probably we do not need a large language model. I think that will be far. But there are a lot of low-hanging fruit we need to pick first. Yeah. Mm-hmm. Yeah.
Any other questions?
Hi, thanks. For the LIF transistor, you showed that the area decreased by about order of magnitude. Do you have a metric for how much power decreases from CMOS
for the neuron, right?
Yeah, for the neuron.
Right, yeah. So if you look at the paper, I think per neuron, even now for our experimental demo, it's still a micron, 4 micrometer by 4 micrometer neuron. That was already go to a femtojoule, something like that. And we also did the calculation to project when you use advanced technology node. Go to 3 nanometer technology node, we can go down to attojoule. Yeah, so that will be actually comparable or even lower than the bio. Yeah. Mm-hmm.
How do you perform the plasticity experiment?
For the last part or which part?
The second part. So you showed some 6 different principles of neurons which are satisfied by the artificial neuron.
Right. So there was some intrinsic plasticity, you mean? The intrinsic plasticity, or so you mean?
No, after this.
This one.
This
right?
one.
So you talk about this.
Yeah.
Right, so that's the intrinsic plasticity. That is a neuron, not synapse. We know synapse can have, the plasticity. Synapse is just learning. So this is a neuron, meaning, it fire from one fire cycle to the next fire cycle. If the next fire cycle is close, then the firing behavior threshold, everything will be slightly different. Basically, the neuron, if it fires frequently, it has a history innate. But if you next firing event is after a long time, then it forget that effect. So that is the intrinsic plasticity we talk about. It's intrinsic inside of the device. We don't need to do anything to get it. We just need to build a device like our bioneuron using ions. It will be automatically there. So that is the way we say understanding by building. Because if you have something like a diffusive memristor, they share the physical mechanism at a physics level with the biological component, then automatically you get multiple properties you're looking for altogether without having to engineer one by one, engineer this one, lose another one. Right? So that is the philosophy. If you make it similar, you will get similar function, multiple.
Great, thank you for the talk. So you did a great job of showing the applications when you have a mature technology that you can fabricate at scale and what you can do with like 2 of an emerging technology. Do you have a sense for what the low-hanging fruits are once that emerging technology gets to like 10, 100, 1,000? Like what is the kind of opportunities in the gap between this brand new technology and something that's kind of more mature?
So you are talking about more like the AI accelerator or the
whatever you think, like what is the best thing you can do once you have 10 to 100 of some new emerging technology?
So this is not specific. I don't know how to. If we think about the AI accelerator, right? So we can show order of magnitude higher energy efficiency. Than GPU, for example, right? Then you can find a lot of edge applications. You use it in the Google Glass, you use it in XR, and you use it in wearables. And those are all the places you require 2 things. One is low energy because it's energy constraint. And second, you want to process information in real time, high throughput. And those fit such technology, perfectly well because that's its advantage. For a longer term, if you also have the natural intelligence emulator part and capability, then the robotics, much smarter robotics that can learn from the environment by interacting with the environment, and it can learn without using backup propagation. Those will all be possible. And but that still, I think, is a little bit far. But even with the AI accelerator, we actually start to use our chip, the SoC chip I showed you, to develop some algorithm that is simple enough, but also general enough. It can be applied on a single SoC and perform learning and planning all on chip, so that it can already fly a drone or something. So those are all the things can be used. Yeah.
Thank you.
Yep.
Okay, one last question.
Given that you did a really good job motivating the problem that you're trying to solve, the energy consumption, also just the growth of AI. And I was wondering, you covered briefly some of the alternative approaches, and I assume there are many. I was wondering if you could maybe shine a light on what are some other approaches to in-memory computing that could also be very promising and should be investigated more.
So other technology, you mean the technology to use it in memory computing or something outside of in-memory computing?
I think better described as like other approaches to doing
Okay.
it outside of Memristor. Or
Right, yeah, okay. So outside of Memristor, we can use other type of devices. I know there are many promising candidates, like ferroelectric, MRAM phase change, and some of the new devices like Belgi working on ECRAM, so those are all very interesting possibilities as building blocks. But outside of in-memory computing, I know there are other types, quantum and using photonics. Those are all very interesting as well. It's out of my expertise. I don't want to say too much on that. Something I don't really know much. Yeah. Mm-hmm.
Thank you.
Yeah.
Great. Thanks a lot
Yeah.
for the great talk. Let's help me thank
Thank
the
you.
speaker again.